All right. Hey everyone. Can everyone let me know if they can hear me? Awesome. Okay. So welcome to the first Organic Chemistry 1 weekly review. We will meet at this time every single week, Tuesdays from 2 to 3:15. Sometimes we might end early, sometimes we might end exactly on time. And I'll be here a little after a while if you guys want to stay and ask follow-up questions to the lesson. So I want to start off with the first session with a little bit of introduction. First of all, my name is Shri Arlagata. I am a senior and I have taken this course and I have taught it. This will be my fourth time teaching / taking the course. So I am pretty well versed with everything OChem related. Contrary to many beliefs, I actually really love OChem. I know a lot of people kind of dread it. You guys have heard some misconceptions about OChem, but I truly believe at UTD we have a great program and we have lots of resources and UTD extra help to make you guys feel comfortable with OChem. All right, so how this will work is I will go over basically what you've done during the week of during your class and lecture, and I will only supplement whatever you guys are learning with examples and a mini lesson every now and then to get you guys all on the same page. And there will be some problems every now and then to test your knowledge and to see if you guys are understanding the material. So I just want to make sure you guys understand that this is different to SI sessions. They have their own thing. This is done through peer tutoring. And of course, as you know, there's also PLTL. So please definitely utilize all three resources that the Student Success Center provides. See what best fits you and make sure that it fits your learning style. Okay, so with the introduction, transferring from Gen Chem to OChem, it's very different because OChem is a very unique science and it requires a different approach compared to your usual science classes. Most of you guys are sophomores. Most of you guys have only taken Gen Chem 1 and 2 as your science. And OChem, it kind of exists on its own. Gen Chem and Biochem are very similar, and OChem kind of stands on its own. There's some concepts that transfer from Gen Chem to OChem and OChem to Biochem, but for the majority of the topics that we learn in this class, both in OChem 1 and OChem 2, will be on its own. So that being said, in the very beginning of OChem, there are some Gen Chem topics that we have to review and refresh in order to get comfortable with the organic chemistry language, okay? And if at any point, by the way, you guys have questions or you don't understand what I'm trying to say, please let me know and I'll try to rephrase it in a way that will make you understand better. Okay, so first off, the word OChem, organic rather, means carbons. So pretty much everything you deal with in organic chemistry. Sorry, let me see, I forgot my video isn't on. All right, can everyone see me? I apologize if there's a little bit of background noise in my house. It's kind of a little bit crazy right now, but I'll try my best to keep it organized for you guys. All right, so like I said, in OChem, let me show you guys the periodic table. So in Gen Chem, you use the periodic table a lot. In OChem, you won't have to use it as much as you needed before. So carbon, like I said, is the most important atom in OChem. Then we have nitrogen, oxygen, okay, and then fluorine, chlorine, bromine, iodine. What is this row called? What is the seventh row? It is your halides, also known as halogens. And then, of course, we have your noble gases, okay? Also, if at any point you guys have questions, you guys can also use the raise hand option, or feel free to use the mic or um, type in the chat. And once again, this session is being recorded. I don't fully know if the chat will. Okay, yeah, it says the chat is also recorded. So anything you say in the chat is also recorded. So because it is recorded, you might want to be careful when talking about grades or professors and whatnot. Okay, so that being said, let's get back to it. So carbon, nitrogen, and oxygen, these are probably your three most important atoms. And then your halides or halogens. And then underneath oxygen, we have sulfur. Underneath nitrogen, we have phosphorus. And then underneath carbon, we have silicon. Okay? Now, and then let me draw your periodic table. Okay? Sorry, I know it's not perfect, but please be patient with me. So you guys have also learned a lot of periodic trends in Gen Chem. In OChem, this is the only periodic trend you need to know, and it's called. There's an acronym for it. It's called BEAM, which stands for Basicity, Electronegativity, Acidity, and nucleophilicity. Okay, nucleophilicity you won't really touch on until exam 2. Electronegativity, acidity, and basicity is probably the most important ones you have to know. Acidity and basicity will follow you to the end, like the final exam of OChem 2 even. Okay, acidity and basicity are that important. They are a reoccurring topic and concept that you'll have to understand. But the good thing is, if you understand this unit, you will pretty much understand it every semester or every unit. Okay? Now, as you know, each corner means that's where it's strongest. So basicity, if you go up to the left, it increases. Electronegativity, if you go to the right and up, increases. Acidity down to the right, increases. Nucleophilicity down and to the left. Okay, once again, do not worry about nucleophilicity. That is a exam 2 topic, and we are trying to learn only exam 1, chapter 1 and 2 today. Okay, and just a refresher, chapter 1 and 2 in your organic chemistry textbook is introduction, is chapter 1, and chapter 2 is structure and bonding. Okay, so this is kind of a general idea of how the periodic table is and how you have to use it differently from Gen Chem to OChem. Okay. Now there are a few atoms here, or elements here and here, but you necessarily don't have to worry too much about it. Okay. All right. Does anyone have any questions so far? Okay. Give me one sec. Okay, so just some housekeeping. I will have to clear my whole board. So if you ever don't want me to clear the board or you want me to wait, I'll give you guys a second so you guys can copy it down or take a screenshot or whatever you want to do before I erase. So I'm about to erase. If I don't see any objections, I will go ahead. Okay. So now I kind of want to go a little bit about the general topics that you'll discuss. All right, sorry about that interruption. So like I was saying, I will go over resonance. Okay, resonance is very important for your first exam. Line angle drawings, which we'll talk about during this review. Okay. Sorry about the messy handwriting. Line angle drawing nomenclature. And some of these you might not have heard of it, but you will within the next week or so. I'm just kind of giving you guys a refresher or a preview of what's about to come. Okay, nomenclature, hybridization. I'm sure you guys have already heard of it in Gen Chem. It is very important in OChem as well. I'll just abbreviate it as hybrid. Okay. Functional groups. Functional groups is important. You'll pretty much use, besides those elements that I showed you, you'll use your functional groups a lot. I'm not sure how much you guys have learned in Gen Chem. I don't think you've learned a lot. It's pretty much like ketones, aldehydes, carboxylic acids. Some of these you might have heard, some of these you haven't yet, but we'll talk a lot more about all this. Okay, so that's kind of a general guideline, if you say so. And let me see if I'm forgetting one thing. Obviously, acidity. Acidity is, once again, it's apparent in every chapter. All right, so acidity, like I said, it's in every chapter. So let's get started with the line angle drawing. So in Gen Chem, you guys learned a lot about Lewis structures. You started with Lewis dot structures, then you went to Lewis structures. Now you'll get into line angle. So for example, each line is a bond, okay? And a bond is, the connection, the shared electrons between two atoms, and each bond contains two electrons, okay? So imagine that there are 2 electrons in every single bond, okay? And then each carbon, as you know, should have 4 bonds. And sorry, I say as you know, but I forgot to mention that. So those 3 atoms that we talked about in the beginning, carbon, nitrogen, and oxygen, you want to make them happy, especially carbon, because this is literally the subject of carbons. Everything you do deals with carbons. So carbon wants 4 bonds and 0 lone pairs. Okay, if it has that, it's very happy. Okay, nitrogen wants 3 bonds and 1 lone pair. Oxygen wants 2 bonds and 2 lone pairs. So it's kind of counting down. Okay, so 4 bonds, 0 lone pairs, 3 bonds, 1 lone pair, 2 bonds, 2 lone pairs. Okay, so these are your ideal like happy atoms. Okay, you want to keep them happy. Okay, if something is missing from these, if carbon doesn't have a bond, or if oxygen has too many electrons, that means the formal charge is going to be either negative or positive. Okay, and that means they're unhappy. Okay, so a little bit of Gen Chem review still before we get into OChem. So like I said, this is your line angle drawing. Somewhat. I'll slowly get you guys into that. So every carbon wants 4 bonds. Okay, so for this carbon, actually, yeah, okay. For this carbon, it already has 2 bonds, correct? It has a bond to this carbon and has a bond to this carbon. Okay, so how many other bonds should this carbon have that we need to draw? Does anyone know? If it already has 2. Yeah, so it needs 2 more. Also forgot to mention that every carbon, well, not every carbon, but each carbon almost always has hydrogens, and if you don't see the hydrogens drawn, that's because in OChem they don't draw hydrogens, so you have to assume it, as well as lone pairs. Lone pairs aren't always drawn, you have to assume it. And carbons are actually not drawn either, but we'll get to that. Okay, so if this carbon requires 2 more hydrogens, these 2 carbons are also inside, while this one and this one are on the outside. Okay, so if it's a carbon that's inside, and that's also bonded to 2 other carbons, these are also going to have 2 missing hydrogens. Well, not missing, but not drawn. Okay, which we'll go ahead and do that. And in the beginning, you might want to physically draw these hydrogens, just so you know formal charge wise, so you're not making any mistakes. But eventually you'll get to a point where you don't need to physically draw every single one, and professors actually don't expect you to draw every single hydrogen. Okay, so just like this, if you notice there's a line of symmetry, that means this one and that one are going to be exactly the same. So this one requires 3. Okay, by the way, just a quick question. Did anyone get my email that I sent around 12 o'clock regarding weekly email? Okay. All right, that's great. Did anyone not get it? Okay. I think I still need to send a few more emails, but don't worry. Next week onwards, I will. I probably won't send it every single week. I hope you guys remember this time. Make sure you guys like jot it down to come. Obviously, it's a little bit slow right now, but once we get going, it's gonna pick up really fast, and you really want to stay consistent in OChem. You can't. It's really hard to cramp for OChem, just because there's a lot of concepts, just like Gen Chem, but it's a little bit easier for OChem. Because personally, I feel like because there's no math involved. If you guys didn't know, there's no math at all really in OChem, so you don't need any calculators or anything. So that's the good news. And OChem is very like practice problem centric, as a lot of classes are, but it's how you study for an OChem exam is how you study for a math exam. Okay, the more practice problems you do, the more patterns you see, and the more quickly you're able to replicate those patterns during an exam or quiz. Okay. All right. So now that we have this line angle structure and Lewis structure a little bit, I'm actually going to draw what you will see in your textbook or lecture or whatever. Okay, so if you notice, I didn't draw anything. Okay, no atoms, only lines. Okay, so every vertice, okay, is a carbon. Okay, and this is what I mean by OChem is a very unique science. Okay, it's not exactly hard, it's just different. That's why a lot of people find it difficult, because it's different, not because it's very complicated. Okay, I hope you guys will eventually love OChem. I know a lot of people do end up liking it a lot more than Gen Chem, but it's just your preference. Okay. All right. So any questions on line angles, or carbons, hydrogens, and like what to expect? Okay. If there are no questions, I will move on. I'm going to erase, by the way. So if you guys haven't already, make sure to jot everything down. Okay. So now I'll quickly talk about resonance, because I know a lot of students struggle with that in the early stages of OChem. So I'm only going to use 3 carbons, 1, 2, 3. And if you didn't know already in lecture, this is how you indicate a resonance structure. Okay. This one and this one are resonance structures of each other. Well, not exactly yet, okay? But once I draw everything, we'll see. Okay. In order for something to be able to resonate, you need a double bond and you need a charge. Sometimes you can actually use a lone pair as well to resonate, but we'll get into that later. But for the most part, you will always see a charge, and a charge could be negative, positive, or a radical. Okay, radical is something important for the next chapter or the next unit in exam 2, but just understand that all 3 of these can resonate, okay, with this double bond. Okay, and they can only do this if they are adjacent to each other, or rather 1 carbon away. Okay, so this negative charge is 1 carbon away from the double bond. Okay, from the carbon that contains the double bond. Okay, and in the beginning, I want you guys to also number your carbons. Okay, and this will make a lot of sense once you resonate. Okay, so I'm going to label it 1, 2, 3, because for each carbon. And now that I have done this, yeah, no problem. Yeah, for sure. Thank you guys for joining in. And if you guys want to finish the rest of the review, you guys can watch the recording. All right, for those of you who don't have class and are still here, I will continue till 3:15. If you guys have any questions, once again, feel free to stop me at any point, raise your hand, use the mic, whatever you guys are comfortable with. Okay. So what we're learning about resonance. Okay, we've numbered our carbons. I've given you where the double bond is, and I've told you where the charge is. Okay. Now to resonate something is to spread that charge across and to make it more stable. Okay. If you are spreading that negative charge across the whole molecule, you are you're diminishing that negative effect. Okay, so it gets less unstable and less reactive and more stable. Okay, so now I'll use arrows to show what I mean and how to resonate. Okay, so each lone pair, by the way, or sorry, each negative charge is exactly one lone pair. Okay, that means it has 2 electrons. So there are 2 extra electrons on this carbon that I am now placing to form a bond between this carbon and this carbon to form a double. Okay, but if I do this, I get this structure. Okay, and what do you think is wrong with this structure? Keep in mind that there is a hidden, well, not hidden, but not drawn hydrogen here. Okay, so can anyone tell me what is wrong with this structure here and why this is not possible? And yeah, both are very good points. Okay, and Octet Rule is something I haven't talked about yet, but it is important when you're understanding resonance structures. Okay, eventually you'll get to major and minor structures, and you have to circle the most stable resonance structure out of your set of resonance structures. Okay, and yeah. The answer I was looking for is what Anusha said. She said carbon has 5 bonds. Okay, and that's a huge mistake in OCHEM. So you never want to do that. If you did that, that means you did something wrong or something else needs to be done. Okay, so because we moved these electrons here and carbon has too many electrons, we have to move this double bond somewhere else. Okay, and we are going to move that onto this carbon. Okay, you always go from atom to bond to atom to bond. Okay, you're never going to suddenly place a negative charge here and the negative charge is suddenly going to go or the electrons will not jump from atom to atom or bond to bond. Okay, I hope that makes sense a little bit. All of this might be a little bit gray area for you guys, might not fully connect, but with a few weeks of practice and lectures, everything will start to click. Okay. So don't worry if things are not making sense right now. Okay. So, but because of this problem, we have to move this double bond also. Okay. And I will draw what it should look like right here. Okay. So the double bond that we formed from here to here, from the red negative charge here, from carbon 2 to 3 is this new double bond. Okay. And then because we took this double bond, remember this bond, every bond is 2 electrons, right? So we took 2 electrons from this bond and placed it onto carbon. Okay. So now carbon number 1 has the negative charge. Okay. I know this is a little slow, but it's because it could be once you learn this and understand what I'm saying within these next 15 minutes, you should be able to do any resonance problems for the rest of your life, essentially. Okay. So let's see what we have. Okay. So negative charge on carbon transformed to carbon 1. Okay. And if you notice, carbon 2 still has a double bond, whether it's 1 and 2 or 2 and 3, okay? So regardless of what structure you guys will get, because this is a very basic structure, but eventually you'll deal with much more complex structures, okay? So always see that your charge is 1 carbon away from your double bond, okay? So if my charge is on carbon 3, I need a double bond between carbon 2 and 1. If my charge is on carbon 1, I need a double bond between carbon 2 and 3, okay? Now I'm going to give you an example where you cannot resonate because it is simply not close enough, okay? It has to be close enough to make that transfer, okay? So let's say, for example, I have a charge right here, and then my double bond was right here, okay? And then let's say I have another double bond right here, and then let's say I have a charge right here. Okay. So can the first charge resonate with this double bond? Let me know in the chat. Okay. All right. A few people said yes. All right. Okay. Yeah. It can resonate because it's close enough. Can this charge resonate with this double bond? Okay. Yeah. Exactly. Yeah. It's too far. Okay. It's too far because it is two carbons away, and we want it exactly 1 carbon away. Okay, and then can this negative charge resonate with this double bond? Yep, the answer once again is no, right? Okay, so the only resonance structure, so if I were to answer this one, let's say the question asked, given this structure, draw all the possible resonance structures and circle the major product, okay? Actually, ignore the major product because it's not going to be different, okay? So make sure to draw your double arrow. Okay, and redraw everything. Make sure you have everything in the same place that you did not touch. And the double bond goes here, negative charge goes here. Okay? All right, so one thing you want to make sure you're doing is each resonance structure will always have the same amount of charges, okay? So this whole structure had a total charge, and I'm using brackets. I think you guys are familiar with this when you do formal charges in Gen Chem. You won't necessarily do this in OChem, but this is for you to understand. So if you notice, both of my resonance structures should have the same equal charges, okay? And then the same here. I see 2 charges. That means I'm going to have -2. And then when I resonated, I still had 2 charges, okay? You should suddenly not go from -1 to +2, -3 to neutral, okay? You won't get, you shouldn't get a different charge, okay? Right, okay, now I wanted to show you why resonance is good, okay? Resonance is really good, in case that wasn't apparent, because when we had charges right here on carbon 3 and carbon 1, both of these are resonating with each other, okay? Now what that looks like is the negative charge exists right here, and it essentially exists all over, okay? Because it is spread across, okay? And because it's spread across on a much greater surface area, the charge has less diminishing value to impact the stability of the molecule, okay? So a structure that has resonance is more stable and less reactive than a structure that doesn't have resonance. Okay, so resonance equals stability. That's the main takeaway if there's only one thing you understood from this lesson. Okay? Does anyone have any questions over anything that I've done so far, especially resonance? I'll give you guys a example problem that you guys can work on for a few minutes, and then I'll go over it. But before I do, any questions? Okay. All right. So once again, I'm going to erase. So if you don't want me to erase, let me know. And just I'm going to use a lot of colors because I personally enjoy that, and I think it helps students learn quicker and connect dots. So if you guys want to also use color for taking notes or using OneNote or Surface Pro or whatever, feel free to. I highly recommend it. Okay, so it looks like everyone's good. I'm going to clear, and I'm going to give you guys 2 resonance problems. Okay, so problem number 1. Let's see. Okay, so what I want you to do is wherever you're taking notes or drawing, I want you to draw all the resonance structures this structure has and then circle the major product. Have you guys covered major product in lecture? If not, I can quickly go over it. Okay, yeah, I can go over it. Let me do both these examples, and then when I go over the problems, I'll talk about major product. So for now, just draw the resonance structures, I guess, and then I'll circle the major products. Okay. I'm gonna give you guys, it's 2:43 right now. I'm gonna give you guys about 3 minutes. Feel free to discuss, um, ask questions, whatever you guys want. All right. So hopefully you guys have been able to get somewhat an idea on how to go about these problems. I'm going to go over them right now. So for the first one, it has 2 resonance structures. I'm going to redraw them. I'm going to post the answers, and then I'll ask if you guys have any questions about it. Okay. And if you guys don't have any questions, I'll move on. Okay. So any questions where I got these 2 resonance structures? Okay. Because looking at it right originally, you might not necessarily think that the negative charge might go all the way here. Okay. So that's why you have to take it step by step. Okay, so this is once you resonate with this double bond, you get this product. And then this negative charge can also resonate with this double bond, so it kind of jumps around the molecule. Okay, as long as the double bonds are next to each other and the charge is also next to each other. Okay. So in this number 1, there is actually no major product, but in question number 2, problem number 2, there is a major product. Okay. So once again, draw your resonance structure. And we only actually have 1 resonance here. Sorry, that should not be here. So it's a negative there, or it's a single bond there and a double bond here. Sorry, give me 1 second. Okay. All right. Yes. Okay. So between these 2, if the question, as a follow-up question to the original problem, let's say this is part B, it asked which one is the major and which one is the minor. This is the major product, and we'll talk about why. And this is the minor product. Okay. For the first problem, all of them are equal. Technically, negative charges and positive charges have their own stability, but that will be discussed in exam 2, so do not worry about that right now. So only example 2 has a major and a minor. Okay. And the reason why this is major versus this, can anyone take a guess why this would be better than this? And let me circle this. Well, they both have double bonds. Carbon's octet. Okay. So the octet rule isn't actually a problem in either of these scenarios. Both of them, well, actually, yeah, the octet is a problem, I guess, but the more apparent reason is what Anisha said about the negative charge being on the most electronegative atom. Okay, you want your negative charge on oxygen rather than carbon. Okay, and it goes back to our periodic table. Okay, so here's carbon, nitrogen, oxygen. Okay, electronegativity increases as you go to the right. Okay, so electronegativity, again, it means it would prefer to have those negative charges compared to oxygen, compared to carbon. Okay, oxygen does not mind holding extra negative charges because it eventually wants to become an ideal gas. Okay, right now it has 6 electrons. It wants to gain more electrons to become, a noble gas. Okay, because of that reason, oxygen is more satisfied with a negative charge compared to carbon, okay? The golden rule is to make carbon happy, okay? Always keep carbon happy, keep carbon neutral, keep carbon with 4 bonds, okay? And I know you can't see it, but this carbon has, if it has a negative charge, that means it only has, or it's missing a hydrogen, okay? So it has 2 hydrogens instead of 3, and here, because of the double bond, now it only has, or it still has 2, but now it has 4 bonds, okay? So because the negative charge is on oxygen right here, it is more stable overall. The structure overall is more stable compared to the whole structure containing the carbon with the negative charge. Okay, and this is the minor product, and this is the major product. Okay, and this is also true if a nitrogen were to hold a negative charge compared to carbon. Okay, does that make sense? Whenever you're deciding major and minor, it's Octet Rule, obviously number 1. Octet Rule is more emphasized than Gen Chem. I would say still obviously look at it, but you won't necessarily see many problems with that rule being broken. And then the charge. Charge means 2 different things. Charge means on most electronegative atom, and the separation of charge. Okay, so you would want 1 negative charge instead of like negative, positive, negative. Okay, because negative, positive, negative technically is also negative. Like, for example, if I were to resonate this, these technically don't officially count, but if you wanted to, you can separate any bond between negative and positive, and it doesn't matter which way they go, at least I don't believe so. But technically, each double bond can separate into negative and positive, because you're technically taking those electrons and putting it onto an atom, okay? That means this carbon will lack those electrons and will be electron deficient. If you're electron deficient, you gain a positive charge. If you're electron rich, you gain a negative charge, okay? So technically, if you were to do this, you have a negative, positive, and negative. You still have a negative charge, but between these 2 molecules, this is more stable because it has the least amount of charges. It has the least amount of unhappy atoms. Okay, to simply put it, you want to have the most happy atoms as you can find. Okay. All right. So does that all make sense as far as resonance? Okay. Obviously, it's going to get a little bit more, slightly more complicated, but just keep practicing. Always, if you ever have trouble with resonance, let's say, God forbid on your exam, you suddenly forget how resonance works. Always refer back to the 1, 2, 3 example that I've shown you, okay? Hopefully you guys have taken notes over it. If you guys haven't, it's in the recording. Always refer back to it, okay? All right. Does anyone have any questions over anything that they've gone over in lecture that they want me to cover or further explain? So we talked about line angle drawing. We talked about resonance. Next, I'll talk about hybridization, because that's also a huge important concept in the early stages of OCHEM. All right. Okay, I'm going to clear the board once again. So hybridization is actually fairly simple because you guys have already done it in Gen Chem very thoroughly, okay? In fact, in OCHEM, you don't have to go too in-depth with hybridization as you did in Gen Chem. And what I mean by this is you used Vesper theory a lot. You don't have to worry about Vesper theory. You don't have to worry about electronic or molecular geometry, bents, trigonoplanar, none of that you don't have to worry about. Like it's a good practice to keep in mind, obviously, but it is not the focus of OCHEM. The focus of OCHEM is to just simply worry about SP, SP2, and SP3. Okay, these are majority, if not all, of the hybridization you have to worry about. Okay, I'm going to quickly run through these because you guys already know it. So SP, remember, has 2 electron domains. SP2 has 3. SP3 has 4. Okay, and if I were to draw, think of X as any atom, it would have, it would look something like this. These are the shapes. And then I drew a circle or oval instead of lines because I want to make sure you guys understand that it could be a double bond, it could be a triple bond, it could even be a lone pair, okay? For example, let me see. Or before we move on, the bond angle, excuse me, is also very important for hybridization in OCHEM. SP is 180, as you guys know. SP2 is 120 degrees, and 4 is 109.5. Okay. And then yeah, the example would be a carbon with the hydrogen bond and triple bonded to nitrogen. Okay, and that nitrogen has a lone pair. Okay, so both carbon and nitrogen have a hybridization of sp. Okay, simply because carbon has 1 electron domain bonding to hydrogen and another electron domain bonding to nitrogen. Yeah, hydrogen and nitrogen. Okay, a triple bond and a single bond, but still sp. Okay, while nitrogen has a lone pair and a triple bond, still sp. Okay. All right. So that's all I'm gonna go over for that. sp2 can look like this. Where both oxygen and carbon are sp2. Okay. Carbon has 2 single bonds, 1 double bond. Oxygen has 1 double bond and 2 lone pairs. Okay, but still, they're both sp2. And then last but not least, sp3, the most basic one, carbon with 4 bonds. Okay, but yeah, or oxygen with 2 bonds and lone pair, or nitrogen with 3 bonds and 1 lone pair. Okay, all of these are sp2, or sorry, sp3. Okay. I think that should be it for hybridization, honestly. It's very straightforward. I will go over a specific example that shows up a lot frequently, and if you guys understand this, you should be good with both hybridization and resonance. So before I go to that example, does anyone have any questions regarding hybridization? Okay. All right, so make sure you have this information somewhere already from previous notes for right now, because I'm going to erase. All right, so the example I'm going to give you is called a amide. which is a functional group. In a functional group, all it is just a combination of atoms. So this, sorry, let me draw this slightly bigger. Okay. So, by the way, if they ever write NH2, just picture it like how I drew right here. With 2 hydrogens bonded, it will make your life a lot easier. By that I mean you will visually see what the question is asking, and you're able to answer the question much quicker. Okay, and that's what OChem is. It's a very visual thing. While Gen Chem might be a comprehensive and math-oriented, OChem is a very visual and pattern-oriented. Okay, so I mentioned before at the very beginning that in OChem they don't really show hydrogens if it's on carbon. Okay, if there's a hydrogen on any other atom besides carbon, they will show it. Okay, for example, nitrogen, they will show it. Okay, but these carbons, they don't show it. That being said, they also don't show these lone pair. Oxygen has 2, nitrogen has 1. Okay, everything's perfect because it is neutral. You know, there's no negative charge, or there's no positive or negative charge. There's no the formal charge is neutral. However, when they ask you for the hybridization of all of the atoms, let's say this is, let me label these: carbon 1, carbon 2, oxygen 1, nitrogen 1. Okay, so if I were to I'm actually going to ask you guys what you guys think the hybridization of all 4 atoms are. So go ahead and tell me. If you guys know, type it in the chat. Tell me hybridization of all 4 atoms. Carbon 1 is sp3. That's correct. What about carbon 2? Carbon 2 is sp2. That is also correct. Oxygen. Also sp2. Good job. And if anyone is confused how we're getting these, let me know. I can explain it. Okay. Which one are you confused with? Carbon 1. Okay. So carbon 1 is sp3. Remember, sp3 has 4 electron domains. Make sure you count the hydrogens. So that's the mistake you made. That probably answered your question. If you draw in each individual hydrogen for the carbons, it should have 1, 2, 3, and then the 4th one being carbon-to-carbon bond. That makes this sp3. Carbon 2 is sp2 because it has a bond to nitrogen, bond to carbon, and a double bond to oxygen. So 3 electron domains, that means sp2. Oxygen also has 3 electron domains, except it has 2 lone pairs instead of 2 bonds, but still the double bond. So 3 electron domains for oxygen, so it's also sp2. What about nitrogen? Is it sp, sp2, or sp3? Okay. Someone said it's sp2. Do I have any other opinions? Okay, so some people are saying sp2, some people are saying sp3. Okay. So right now, it actually looks like it's sp3, but it should actually be sp2. Okay. And the reason being, now the right answer is sp2, by the way. If this was an exam, please put down sp2. Okay. The reason being is anytime you do hybridization, and I would write this down, every time you do hybridization, you always have to take resonance into account. Okay. Resonance means you have to see if the lone pairs on the atom that you're looking at can resonate. If they can resonate and the hybridization goes from a high energy state to a lower energy state, the lower energy state is the answer that you put. For example, in this case, the amide, the nitrogen in this molecule, amide, the lone pair on nitrogen is next to or adjacent to a sp2 atom. Okay, I'm not sure if they have covered this in lecture yet, but they will talk about it. I'm sure this is like the exception where you have a lone pair on an atom which is adjacent to another atom that is sp2. It will resonate and this becomes sp2 as well. Okay, and I will walk you guys through what that looks like. Okay, kind of drew it big, so I'm gonna draw it slightly smaller here. I'm gonna draw the resonated form and then we can talk about it due to time. Okay, so I'm resonating this lone pair here, and if I resonate it here, the oxygen will have to have an extra lone pair. So originally it had 2 lone pairs, now it has 3 lone pairs, okay? Because, and I'll show the movement of electrons through the red arrow. Okay. Hopefully you guys understand the arrows, why I had to make 2. Every time you do resonance, you always have to make 2 because you're moving both the charge and the double bond. And also, if you want to take a look at this from a different angle, here's my charge, here's my double bond. Remember, this goes back to our basics, the 1, 2, 3 rule. It's actually not a rule, it's just something I came up with, but yeah. Okay. Hopefully this makes sense in relation to that. But yeah, nitrogen has a lone pair. A lone pair, remember, is essentially a negative charge. That charge can come here and form a new double bond. And if that forms a new double bond, this carbon will have too many bonds. It will have 5 bonds. It will break the octet rule. So it has to let go of one of its bonds. And it's going to do that by placing the bond to oxygen, because oxygen is the atom closest to this unhappy carbon, which can accept extra electrons, because the hybridization of oxygen in this structure would change to sp2 to sp3, but the answer we still put is sp2 because we want the lowest energy form. Okay, the oxygen in this structure is sp2, the nitrogen in this structure is sp3. The nitrogen in this structure is sp2, the oxygen in this structure is sp3. In however many resonance structures we get, in each of the resonance structures we want the lowest energy level. Okay, so sp2 is lower than sp3, so the answer is going to be sp2 for oxygen. That's a very good question, actually. Okay. So because of that, every time you do hybridization, you always have to see if it can resonate. If it does, is it going higher or lower? Okay, if it goes higher, you keep the lower one. If it goes lower, you keep the lower one. So you always want the lowest energy form. Okay? Hopefully that made sense. So in both forms, you would say oxygen is sp2. Are you saying it like, yeah, if they give you either of these, the answer would be sp2. But technically, this is sp3 in how it looks like right now. But you can easily fix that by resonating back into this form, okay? Just because they give you one structure, it does not mean you have to take it how it is. You can resonate it to become lower form, okay? Okay. And for those of you who didn't make sense, I can cover this again for the next week. I'll start with this topic since we're about to get close to the ending time. And yeah, I also want to quickly go over bond angle and orbital of the lone pair. This orbital, do you guys know what localized and delocalized mean? Localization and delocalization of electrons. Okay. Okay. Well, it should have been a Gen Chem 1 or 2 topic, but basically it means that if your electrons are localized, that means these electrons cannot move. Okay. But if they can move, meaning that they are resonating, they're moving across molecules and atoms, that means it's delocalized. Okay. If you have delocalized electrons, that means your electrons, if it's delocalized, that means it's resonating. If it's resonating, it means it's delocalized. And if either of those are true, that means the orbital this lone pair is in, or this lone pair is going to be, actually, let's just focus on the nitrogen lone pairs. The nitrogen lone pairs will be in the p orbital, okay? Resonance or electrons can only exist in a pi bond. Well, every double bond is considered a pi bond, and each pi bond has p orbitals. Okay, and electrons can only exist in an unhybridized p orbital when they resonate. Okay, and I will draw that fully, and also I'll re-go over this during the next week's lesson in the interest of time to further explain this, but I'm going to give you guys the answers. The next question that they might ask is the bond angle between carbon, nitrogen, and the lone pair. And your answer would actually be 90 degrees, okay? And this is a very visually difficult question to grasp, and so I will have to use different drawings and examples to show that. But that's it for today, for this week. Next week, we will go over, we'll review everything that we've done this week as well as continue forth. I think next week you guys will start talking about alkanes, and the week after that is geochemistry. But yeah, we'll continue this every week. Okay. Do you guys have any questions before you guys leave? It's going to be a little bit slow in the beginning, but it will pick up, and you guys will start to understand OCHEM and make things click a lot better. Once again, this will be recorded. You can find it in there should be a recordings in one of the tabs. and I think it will also be eventually posted on YouTube. When that happens, I'll let you guys know. But yeah, that's it for today. I hope you guys learned something. Remember, resonance is important. That's the main takeaway. I think I said something else, but yeah. All right, well, I'll see you guys next week. Take care.